My next guest, Assistant Professor of Computer Science, Aaron Solovey of Drexel University, and Senior Researcher Andrew Bagel of Microsoft Research. They're using some amazing tools with the goal of improving our performance on various tasks. Just remember, Aaron and Andrew aren't really mind readers, even though they've got these cool devices here. So if you have questions, we got to do it the hard way, the old-fashioned way. Type it into the chat window. You've got the tool right there in your viewer. You do that. Aaron and Andrew, thanks for being here.
Thank you.
We are putting research in focus. Your segment has a title, so no pressure there, all right? So I'm told, of course, that you're working on complementary approaches for using psychological, physiological data to predict cognitive workloads. And Aaron, I want to start with you. In your work, I understand you're studying the impact of cognitive workload on people doing commonplace but potentially dangerous activity, driving. Explain why you chose driving.
All right. Yeah, there's lots of reasons. So as we know, driving's the dynamic task that we do. It involves visual, manual, cognitive load that you have. So you have to determine where you're going, which is a strategic goal. You have to monitor the road and also your vehicle, and that's more information processing. And then there's the physical act of actually manipulating the steering wheel and doing the physical driving. And so there's a lot going on. And then also we've been seeing this, there were, I think, 387,000 injuries from distracted driving in 2011, and over 3,000 people were killed. And a lot of this comes from the secondary, other tasks that people are doing while they're driving. So you have the driving task plus the secondary task. So what I've been trying to do is study the workload that is induced by these secondary tasks, because I think it's important to understand that driving's changing a lot. We have GPS system, we have browsers even in cars, and also, so this is a
picture of it in action.
Yeah, well, that's in a simulator, yep. And so, plus people are bringing their technology into the car, which adds extra workload. And then at the same time, cars are becoming more advanced. So we have more automation in cars, and this can change the role of the human in the vehicle from the manual control to someone supervising. And so understanding the workload and how that's changing as cars evolve is important.
Wow. Okay, so you're trying to work to understand when a driver's workload is either overloaded or underloaded.
Exactly.
And you're using something called what? FNIRs to study brain activity.
Yep. So FNIRs is one of the tools I've been using. It's a brain sensing tool. It's been used more recently, and it measures blood flow and blood oxygenation, which is similar to what an fMRI measures. But it's portable, non-invasive, pretty easy to use, and so we can get this information about your cognitive state while you're driving.
And see, you brought a little toy with you.
Yeah, so this
I must ask you to fashion it. I mean, show us what it does and what's its role with FNIR.
Okay, I'll put it on for a moment.
Come on, all the kids are going to be wearing these this holiday season.
Yeah, so this is actually a device. This isn't what I've been using more recently in studies, but this is one that we put together for earlier studies.
Okay.
And really, the way that it works is, can I take it off?
Yeah, yes. Be humiliating. Sure. Yes.
So the way it works is in these. In here, the reason we have this is there's little holes to put light sources and light detectors in here, and they hold them in place on your forehead. And the light goes into your forehead, and your bone and tissue is transparent to light at these near-infrared wavelengths, and it's the oxygen in your blood that actually absorbs the light. And so we have the light sources going in, and then there's detectors that are embedded into there that can detect how much comes out, and from that we can calculate how much oxygenated blood is in that part of the brain, which is an indicator of brain activity.
Wow. Okay, so this headband's reading the level of brain activity in the person who's wearing it. Is this the only data input you consider, or are there others?
No, so this is one of the things I've been using. I have also done work with EEG brain sensing, but more recently I've been also looking at physiological measures, so body sensors, looking at heart rate, skin conductance level. And then in addition, I also look at the task that you're doing and any context information we can get from the task. If you're using a computer while we're sensing you, we can also see what's going on in the computer. If you're driving, we might be able to use the sensors in the car and use all of that to get a better figure out your cognitive state while you're driving or doing your task.
And talk about your actual process. Is it all simulators, or is there people actually on the road?
Yeah, so I have done both. So far with the brain sensing, I've done it in a simulator. So you saw the picture earlier, which was someone wearing FNIRs in a car simulator. And so we had a full car, and then there's a screen in front of you. But all of the steering wheel, there's a pedal to accelerate. It's all active, and so you can use that. And then with the body sensors, the heart rate, skin conductance level, we've done studies on the road in an actual car on the highway, where we gave people drove, and then we gave them a secondary task to do. And we did a pretty large study with 100 people, over 100 people on the road. And trying to see if we could use these body sensors to determine their workload while driving.
Wow. Okay, so you're getting all this data in. What do you do with it? I assume this is where machine learning comes in.
Yeah. So exactly, what we'd like to ultimately be able to do is use these sensors to automatically determine your current state. And so to do that, one of the tools we use is machine learning. But in order to do that, we need to build up big data sets with the brain and physiological data. That's labeled. So we need labeled data. And so a lot of my studies have been building these data sets where like I said, we had 100 people on the road, and then we gave them a task that has a known level of workload. We use tasks that have been studied in psychology for years, and those have a known level of elevated workload, and then we'll also have them just driving. And then we can build these data sets that say, this is what your brain and body sensors look like when you're driving alone, and this is what it looks like when you're doing a secondary task. And then that can be used to build a classifier that when we don't know your current workload, we can use that data to classify it.
This is fast. I'd love to put this on my head to see
Go for
what it is I'm thinking about. No, not right now. Those moments that we've all had where all of a sudden you discover yourself on the road, many blocks or even miles down the freeway from where you were when you last checked out in your brain. Where am I? How did I guess this part of my brain kept driving and this part of my brain was on something. This is fascinating stuff. And Andrew, I want to bring you into the conversation. I understand you're using similar devices to measure psychological, physiological activity, but instead of studying drivers, you're looking at computer programmers. So what is the goal of your research?
So my goal is to look at when computer programmers get stuck or confused with the software they're working on that they're actually writing. Like, for example, at Microsoft, we build a lot of software, and we have about 30,000 engineers that work on that software. And sometimes, rarely, bugs make it into the software that we ship. And those bugs have to get fixed, and that's expensive. So with my research, what I'm looking for is a way to detect when the programmer is about to cause a bug and stop them before that bug can enter the code.
Wow.
And what my theory is basically that I can start using some of these devices, and actually you can see some of them here.
I got to get one of those, by the way.
To figure out whether the programmer is confused or frustrated with what they're doing. Maybe that's not the time that they should be actually typing code. Maybe they should go ask a question of somebody else.
Okay, so are you actually measuring the same kind of physiological, mental responses as?
So I'm using a slightly different set of sensors. So the one on my wrist here, this is a Shimmer 3 GSR Plus sensor, which is basically measuring how much sweat I'm putting out on my skin, which is a measure of arousal, how much I'm paying attention to what I'm doing.
Right.
So if it's a low signal, I'm kind of probably just came back from lunch and not really paying attention. Maybe that's not a good time to be coding. We also have this sensor. This is a Nico Mimi set of cat ears. Over here on the front is an EEG sensor. And the EEG sensor is placed against the forehead, where it's basically measuring basically one part of the prefrontal cortex on the left, and then there's a little ground that goes in your ear.
And nobody will even know you're wearing it.
And then the ears kind of flick back and forth to show basically the ears, if I'm really paying attention, the ears will pop up. And then if I'm super calm, they kind of relax and the ears go down.
Wow.
This is built for the Japanese market. So it's
I could certainly see the social value of hey, that person likes me.
We tend to use the ones without the ears, so we can plop the ears off. Actually, you could buy new ears for it if you like to be fashionable.
Accessory business.
Which is kind of cool. So we've got those kind of ears. And then what we also do, we've also been using eye tracking. So this is where the computer itself is projecting infrared light at your eyes and trying to figure out where your pupil is. And then it knows how far you are from the screen, and using geometry, it can figure out what exactly are you looking at on the monitor.
Wow.
So when you're programming, we want to start, and you get confused, we want to find out, it was that class or that method over there that got you confused, or that was the trigger for you getting confused.
I know we actually have some video of all of this in action. We're going to roll that video, and we can take a look here.
Great.
So what are we seeing here? This must be the eye tracking.
This is a Visual Studio programming environment. The little red ball that you're following is where the subject is actually looking on the screen as they look at that code.
Yeah.
And we've asked them to just read the code and there's a question at the bottom of the code that it draws two rectangles, and they're asked if these two rectangles overlap. And and now you can see this huge red dot. That means the person stared at that one spot on the screen.
Wow.
Because that was particularly confusing or particularly difficult for that person. He's actually doing it multiple times before he starts reading the rest of the code. You can see a picture-in-picture of the subject in the bottom of the screen there. And this particular thing actually was kind of difficult, just because it was sort of spatial relations for most people. It's just actually kind of difficult.
So you're using machine learning algorithms to draw conclusions from all the data you're getting here.
Yep.
Explain the process of machine learning that you're employing.
So we're trying to build a bunch of different classifiers to tell, is the person experiencing difficulty? Did they feel that what they're doing is tough for them? So we had a whole lot of people come in, about 15 people come in and do 8 different tasks. Each person took about an hour and a half to do it. While we were measuring their EEG, watching their eyes, also measuring this on the GSR device on my hand to measure how attentive they are. And then we take all those signals into our machine learning environment. And what we were doing is trying to predict 3 things. One was, if we watch 14 people do this task and then we take the last person, can we predict, as the person is working, is that task difficult for that person? It doesn't work that well. What works better is if we say, well, we watched everybody else do this task. If we then watch a new person do this task, can we figure out what's going on? And then, in fact, we do really well in that kind of environment. So we're trying different combinations of that to get a classifier that will actually run as the programmer is working, where in real life, you don't know what the task is. Like, the person is just supposed to be working on a bug or writing a new feature for their program. And there's no beginning, there's no ending. It's just kind of like, it's getting hard, it's getting easy. But when it does get more difficult, that's the point where we want to try to intervene in the programming environment and do something to either make them pay more attention or maybe to get them to stop or slow down or maybe ask a question of somebody else.
So you're studying, programmers, you're looking at drivers. If we've stuck this on somebody driving who was trying to write code, would this just catch on fire? Is that what would pretty much happen?
They would get stopped by the police.
We have a big online audience joining us today, and one of them just wrote into you, Aaron, says, what type of secondary tasks did you analyze? They want to know, talking, changing music, texting?
Yeah,
that's a great question.
Yeah, it's a good question. So we've been using generally a lot of working memory tasks because we're thinking about someone who's driving and maybe trying to, whether that's involved in having a conversation, it's also if you're trying to remember the direction somewhere, you have to store something in working memory. So there's a task called the NBAC, which is used a lot in research, where you have to, so this is a proxy for a real task, so I don't imagine anyone would actually do this in the car, but this you can set it up so that you hear a series of numbers and you have to respond with the number that you heard to previously from the one that you just heard. So you're listening to the information and storing it in your head, and then so as you hear these numbers, when you hear, you have to remember what you heard to back and then update it. And so this has been used in lots and lots of studies, and this is really just to calibrate the system and say this is what a working memory task would look like. And it's not realistic for something someone would do, but we can then train a classifier using that can then look at other tasks that you're doing and see if it looks similar to when you're doing that elevated cognitive task or not.
Wow.
Yeah.
This is wild. It's fascinating stuff. Thank you both. Unfortunately, we're out of time. If I had that on, the ears would have gone, out of time for the segment. Thank you both very much.
Thank you.
Thanks for stopping by, explaining remarkable advances in this technology. It's really fascinating stuff. Thank you both so much.
Sure,
Thank you.